All right, so in those last examples, I was sure to underline in chlorination how reactive those hydrogens were. And that's because there is a difference between chlorination and bromination, okay? An interesting issue of selectivity. So when we take propane plus chlorine, again, we throw in some H nu, told you we get 60% of this guy and 40% reacting with that primary hydrogen, forming the primary radical. We do make HCl, but importantly here, this guy is our major product. Okay, he's the most abundant. Well, when we take propane and bromine, Br2, we get a different product ratio. Okay, so we actually get 97% of this guy and only 3% of the primary. And we make HBr, of course. But this is definitely a much better selective reaction. Much better, improved selectivity, right? Because instead of this almost 1-to-1, I know it's not 1-to-1, it's whatever it is. It's not 1-to-1, but it is greater only by a little bit, 60 and 40. We get 97% here. Ugh. So where does this selectivity come from? Why is it so different between the bromine and the chlorine? And the answer belongs in those first two handouts we saw, kinetics and thermodynamics, okay, from chapter 4. Okay, so the bottom line is that the rate determining step of bromination is endothermic, while that of chlorination is exothermic. So we're going to go through and calculate this. Okay, again, we're not just talking about methane, so the calculations for the delta H's are going to be different. And so the key step of bromination then has a late transition state, while that of chlorination has an early transition state. Okay, so we're going to see what this looks like. But first we have to calculate our enthalpies. All right, our chlorination. Prop step 1. Remember that was the rate determining step, even with methane. So it's true here also with propane. This is our rate determining step. All right, what does that look like? We have that secondary hydrogen reacting with chlorine dot in this fashion, right? We have this reacting, and then we have electron staying behind. So one electron goes and forms a bond with the chlorine to make HCl, but then one electron also stays behind to form our more stable secondary radical. Okay? Or, right, it can make that primary one. Those are our two options. Okay, so let's show that. Okay, so again we make HCl and our primary radical. Okay, so in each of these cases, what was broken and what was formed, which bonds were broken. In this guy, it was a secondary CH, and that is plus 95 kcals per mole BDE. And in this guy, it was a primary CH, and that was plus 98 kcals per mole. Okay. And in terms of formed, both of them, we form HCl. So they both will have a value of negative 103 kcals per mole. And so again, HCl, negative 103 kcals per mole. Because they're formed, so they're negative, okay? So then delta H here is negative 8 kcals per mole, because right, we just add them up. Or we subtract this amount from that amount, okay? So we get negative 8 kcals per mole, and the delta H here, negative 5 kcals per mole. Okay, so that secondary radical formation is actually a little bit more exothermic, but importantly, these are both exothermic. Wow, I don't know how that happened. They're both exothermic. Okay, so what about bromination? Let's compare those energies. Okay. bromination, prop step 1. Again, that's still the rate determining step. Okay, so again, let's just go and show it. This hydrogen is reacting now with a bromine dot. Okay, to form HBr. And again, a secondary radical. Or, right, we can form the primary. Going and reacting, okay, to form HBr plus that primary radical. All right, so what bond was broken here? Again, it was a secondary CH. Okay, so again, this was plus 95 kcals per mole. And then in the primary, again, it's similar, it's the same, sorry, plus 98 kcals per mole. But now what's different in terms of forming, we form HBr instead of HCl. Okay, so we form HBr. And this is actually only negative 88 kcals per mole. Okay, again, HBr, negative 88 kcals per mole. Okay, so if we go and do our math, the delta H here is actually positive 7 kcals per mole. And down here, it's actually more, equals plus 10 kcals per mole. So importantly, here, again, they are endothermic. Okay, which means when we draw their reaction energy diagrams, they're going to be slightly different. Okay, so with the chlorination, again, it's exothermic, and in the bromination, it's endothermic. So I just went through and calculated that and showed you guys that that was true. So then all we have to do now is remember the Hammond postulate. That was the last time we saw this early and late transition state. Remember the Hammond postulate. Okay, so what is this going to look like for chlorination? Okay, it's going to be exothermic, right? And as we saw, right, the secondary radical, that step was slightly more exothermic than the primary. Okay, so the product, again, of that intermediate step, so this is reaction progress, and again, this is prop step 1 only, step 1. Okay, so we're going to be exothermic, and let's label this one as our primary radical. Okay, and then our other possibility here, it's going to be a little bit more stable, right? So now we have our more stable secondary radical. Yes, both of them make HCl plus HCl. And over here, we should have propane plus Cl dot. Okay, and remember these guys were different by only 3 kcals. 3 kcal difference. That can be seen up here. The difference between here and here. Just 3 kcals. Okay, and again, it was the secondary radical that's a little bit more stable. Okay, well, in bromination, okay, it's going to be endothermic. So let's go through and label all of that. Energy, again, reaction progress, and prop step 1. Okay, so we're going to be endothermic. And let's draw the more stable one here. So this is the secondary radical plus HBr. And so the other one, the primary radical, it's going to be a little bit higher. Okay, so here we get the primary radical plus HBr. And so again, these guys' difference, 7 and 10. So again, they have a difference of 3 kcals per mole. Different Okay, so then what this actually ends up happening then is because we are closer in energy at the transition state, right? The transition state. Here it's later, so it's more like the products where there is a full-blown 3 kcals difference in energy. Whereas over here, we're more like the starting materials, right? And again, we only have one set of starting materials, so actually the difference here is going to be smaller. Okay, so the difference here, again, the difference in energy between the two routes is going to be smaller than it is here. Because again, this is closer to products where we have the actual difference. Whereas here they're closer to products, here they're closer to starting materials where there is no difference in energy. Okay, so if we actually drew this out and I drew it to scale a little bit better, here it's only about 1 kcal difference in energy. Cal difference in energy. Okay, whereas over here it's going to be a little bit bigger. Okay, so here it's going to be 2 kcals different. Okay, and that's again because it is a late transition state. Okay, it is a late transition state. Okay, this energy of the transition state is closer to the energy of the products, closer to energy of products. Okay, therefore there's a larger difference in energy. Larger difference in energy. Okay, and it's this larger difference in energy then that is the source of our selectivity. Okay, because again, because it's but because there is a slightly more stable path than here they're like closer in energy. Okay, so it doesn't really matter which path, okay, because they're so close in energy. But here they're a lot more different in energy, and so it would rather take that more stable path more of the time. Okay, again, that's because it's a late transition state. It looks more like the products where there is a difference in energy. So the difference between the two paths is going to be more pronounced than it is here. So here we don't really care as much, whereas here we want the more stable path more of the time. Okay, so I'm going to write that. This larger difference in energy makes bromination much more selective. Okay, and so pretty much only the most stable radical is formed. Okay, so a lot of these problems in your homework are saying provide the major product, provide the major product. Well, with chlorination you're going to get more mixtures than in bromination. Bromination, pretty much go for the product that is formed from the most stable radical, and that's going to be your go-to product. Okay, so as it says here, in chlorination the transition state is more like starting materials and the carbon atom involved has little radical character. In bromination the transition state is more like the full-blown radical and the carbon atom has a great deal of radical character. So the difference in radical character is relayed in the selectivity of the reaction, and thus bromination is more selective. So that's what I'm saying. I'd much rather go for the more stable path more often. Whereas here they're closer in energy, so it doesn't really care as much about the path, okay? Because again, it's closer to starting materials. Whereas here we have more radical character, so it's going to go for the more stable radical more of the time. Okay, so this is generally true. Exothermic processes tend to be less selective than similar endothermic processes. And again, it's because that difference in energy at the transition state. It's going to go for the more stable route more of the time. Okay, it's going to form the most stable radical, and that's because it's closer in energy, so the energy is more pronounced. Awesome.